All right, everybody, welcome back. Couple of announcements that you'll need to know about. I did send an email last night that has a lot of the material in it, but just as a reminder, your presentation topics are due to your teaching assistant by midnight this evening. So please ensure you have that to them today. If you haven't already done so, please ensure you have that to them. As a reminder, that topic can be anything in the world because everything has some degree of chemistry in it, whether it's in the manufacturing or it's in its use or it's in its decomposition and problems with it or whatever. So there are a myriad of topics. Find something that is of interest to you, do a couple of things that are of interest to you, and send your presentation topics to your TA. After problem set quiz 1, question 4 was a question on what concepts do you find confusing, difficult, challenging, that type of idea. I did read through all of that, and in reading through all of that, the general observation for most people was that you were still confused as to how to actually go about doing it, what reaction orders mean, and that type of idea. I normally present a visual, and I will explain how we're going to do that in a bit. But the answer to setting up and solving these things, it comes with practice and the like. There wasn't any overwhelming one thing that everyone had difficulty with, is the take-home message I got from it. And just with practice and asking questions, the chat, the discussion forum, that type of idea, people will be able to get more comfortable and confidence with it. In the future, for answering that question, if you were to put your responses in point form, like bullet form, either one per line or put a comma between them, that makes it so much easier to create a visual representation of what people find difficult and challenging, and then I'll be able to present that back and close the loop with students. One other thing that came up in the previous class is that apparently you have, an experimental report due on Monday, and you had a quiz due Monday, and some people actually work on the weekends. And so I had received a request that was backed up by a number of students to maybe extend the problem set quiz by a day or something like that, and I agreed to do that. So I have moved the deadline for the problem set 2 quiz to be Tuesday at midnight, not Monday at midnight. And finally, with regards to the use of Collaborate, it's very slow on my end. So I am going to be putting people in breakout rooms, and my functionality in bringing you out of there, it lags a lot on my end. So please bear with me as we go through that. And I try to figure out if there's anything I can do to speed it up or just get more comfortable with it and accept the fact that it takes 20 seconds to put people into the breakout rooms and 20 seconds to pull people out of those breakout rooms. In any case, that's all that I have as announcements today. Does anyone have any questions about what I've discussed before we continue with the course material? Oh yes, one other point that was in the email is this evening, so from about 6 o'clock tonight until midnight on Saturday, there is a survey that's going to, that it will be on the Hayden McNeil website. It's actually in the same location as the problem set 1 and 2 quizzes, and that survey is to figure out which one you prefer. Do you prefer Hayden McNeil? Do you prefer Blackboard, or do you prefer Collaborate? Try that again. Do you prefer Teams or do you prefer Collaborate? And the reason why it closes at Saturday is so that I will tell everybody on Sunday which one we are going to continue with for the remainder of the term. Thanks, Ben. All right, so last day we were looking at this problem. we were looking at the relationship between Kp and Kc, and we derived this relationship presented here. Oh, we didn't actually derive it, I gave it to you, because it's the application that is of interest. And we went through and we did the first problem. So when we went through and set up and solved this first problem, Kp equals Kc RT to the delta N gas. When we rearrange it to get Kc, we ended up having RT to the minus delta N gas. Excuse me. And when we plugged everything in, we got a value of Kc of 273.5, carrying an extra digit through, liters per mole. I left it as an exercise to you to do the other one, to go through and look at the second reaction, which is Kc, and then determine the Kp value for that. Does anyone have their values, their answers that they wish to share? Anybody? All right, well, I'm not going to spend any time on it in class. I will just present this here. This is what the final expression is, and this isn't relevant to that. So the answer for Kp is 0.0687. It will reconnect in a second. Sorry. It should reconnect in a second. There we go. And so this is how that problem was set up and solved. A delta N gas is -2, so on and so forth. And I will leave you with that. And we are going to continue. What we're going to do now is we're going to look at the magnitude of the equilibrium constant, given that we have, as presented here, R is in equilibrium with P, reactants are in equilibrium with products, and we have the equilibrium constant P over R. So what I want to get from you is, what is the magnitude of the equilibrium constant when the products dominate and the reactants dominate? So what do we end up having? Is K a large number? Is K a small number if reactants dominate and products dominate? So think about that for a few seconds, and then when we call you back, we'll get your responses on this. So I'll give you about 10 seconds. If there's lots of reactants or if there's lots of products, what is the equilibrium constant? K is large when products dominate. K is greater than 1 when products dominate. Good. So yes, and that's kind of just what I was going to present over here. When you have, oops, wrong one. We can look at it when there's lots of products. You end up with a bigger number, oops, over a small number, okay, when products dominate. And this value is, of course, greater than 1, big number over small number. And when the reactants dominate, K would be a small number over a big number. And that is less than 1. Yes. Good. Now, in the extreme, okay, in the extreme, this small number ends up approaching 0. Okay? And when that approaches 0, this expression approaches infinity. Similarly, when the reactants dominate, so when the number approaches small, when the number of reactants basically goes to zero, you've used up all of the reactants, the equilibrium constant approaches infinity. When the reactants dominate and you actually don't produce a lot of product, the amount of products produced approaches zero, then this value approaches zero. So at the extreme, you end up with this number line. And on this number line, you have K ranging, the equilibrium constant ranging from 0 to infinity. At equilibrium constant equals 0, you have a system where the reaction doesn't actually proceed. 0 products are actually produced. The other end, when the reaction goes to completion, all of your reactants are completely used up. And it is possible to be on both sides of that. When the equilibrium constant is small and less than 1, then you have reactants that are favored. There's more reactants than product. Reactants are favored in that reaction. The equilibrium constant is greater than 1, more products are produced, the products are favored in the reaction. And of course, if you have an equal amount of products to reactants, then you end up with, of course, an equilibrium constant of 1 specifically. So I mentioned and showed on the first day that the equilibrium constant is a function of temperature. We haven't done thermodynamics yet, but when we do thermodynamics, well, actually you've had in Chem 100 the concept of enthalpy. And equilibrium favors the exothermic reaction. Whatever the exothermic reaction is, that's called enthalpic control of the equilibrium constant. Equilibrium also favors the side that has the most entities. You haven't discussed, at least in university, the concept of entropy yet. We will when we do thermodynamics, but this is entropic control, the side that has the most entities. And these are two different forms of energy that we're talking about. Sometimes these factors work together, sometimes they compete with each other. And so we have this expression, or this reaction right here. The Haber process is a very important reaction industrially. It produces ammonia, which is a starting material from everything from fertilizers to energy storage to refrigeration units. It's allowed the world population to grow. It's also a pollutant as well, but we'll just realize that ammonia is a very important industrial chemical. I am going to put you off into breakout rooms, and what I want you to do is I want you to discuss amongst yourselves and figure out which side is favored enthalpically and which side is favored entropically. So like I said, I'm getting used to these breakout rooms things. I'm going to put you off into groups, and I'll call you back in about a minute. Shouldn't take that long. So I'll talk to you soon. Bye. Hey, Shamitha.
Hello.
I don't think they can hear us in the breakout rooms, can they?
I don't think so.
I know that somehow I'm able to communicate with them in the breakout rooms, but I haven't found that yet. It took 30 seconds to get everybody into breakout rooms. Good grief.
If you go to the people panel, you can go in and out of each room.
I know I can go in and out of each room. That one I know I can do, but my challenge is if I want to, I give a global announcement saying I'm, pulling everyone back. I don't know how to do that. And it's not intuitively obvious here.
if you put a message in the chat box if they would be able to see it.
They do. They can see a message I put in chat, but I remember having this ethereal voice coming in going, all right, I'm pulling everybody out now. And that's about all.
I don't know how to do that.
Yeah, it's my interface is not smooth. What are we at for time? All right. Oh, I'm going to pull them out now. All right. All right, I'm pulling everybody out now. I can hear myself. And it's going to take another 20 seconds to get everybody back. All right, I think I have everybody back in the classroom. Can I ensure that everyone shuts off their microphones so that we don't get cross chatter and that type of idea? Now, either someone speaking verbally if they wish, or into the chat if you would be so kind as to tell me which side of this is favored enthalpically and which side is favored entropically, reactants or products.
I think that's Jason. Come on,
Jason. Go ahead.
I said that the left side is favored enthalpically, and the right side is no, the other way around. Right side is favored enthalpically, the products, and the left side is favored entropically, the reactants.
Okay, and Mark, your comments?
Sorry, I was just saying that I think the reactants have more entropy because on the reactant sides there's 4 moles of gas turning into 2 moles of gas, so there's more randomness on the reactants. And since the products have the kilojoule, which is the energy, I think it is an exothermic reaction, which means the products have more enthalpy.
And you were both correct. You both say the same thing, different words. The reaction as written shows energy as a product of the reaction. Energy is released as the reaction proceeds to the right. That's enthalpic control. So products are favored enthalpically, but the reactants have more entities. And so it is, the left side, the reactant side, is favored entropically. So this is where there's a competition between enthalpic control and entropic control. And that's visualized in this graph right here, which shows what the extent of reaction is as a function of temperature and pressure. So extent of reaction is like the equilibrium constant in the sense that when the extent of reaction is low, the reactants are favored. When the extent of reaction is high, the products are favored. You can see here that at low temperatures, at 0 degrees Celsius, we basically have close to 100% extent of reaction. The products are definitely favored at low temperature. Unfortunately, at low temperature, you don't get the reaction proceeding. The activation energy is too high for this reaction to actually proceed. It's very much like the iron and oxygen. It would like to form rust, but the barrier to that process is just too high under ambient conditions. This reaction, the Haber process, is run at around 350, 450 degrees Celsius, where the extent of reaction is around 40 to 60, 70 percent. So you're not getting 100% conversion, but you are at least getting some degree of conversion, and then you can just recycle your reagents through the reactor again. Nitrogen and hydrogen are fairly inexpensive. Ammonia is just extracted and the reagents are recycled. So here we have a competition, and like I said, enthalpic control favors the products, entropic control favors the reactants. I'm back. So about the temperature dependence of the equilibrium constant. And if we go back to that slide, we have ambient air, 25 degrees Celsius, we'll use as a temperature. You have nitrogen and oxygen, argon, and all the other chemicals or entities that you know that are in air. But with a lightning discharge, the temperature inside that lightning discharge is literally 25,000 degrees Celsius. It's hotter than the surface of the sun inside the lightning discharge. And that dramatically affects the equilibrium constant. Before I look at the numbers here, I just want to point out that by now you should be able to look at the chemical equation and figure out what the units are associated with that. And so the units are going to vary for each of these ones, but you should be able to understand where that comes from and figure those out. So here in the first reaction, we have nitrogen and oxygen. Nitrogen and, okay, hold on. There's apparently is a problem with lag. Again. Let me just check something here. My connectivity is fine. I apologize for everyone who's got lag. My camera. Weird. I'm just curious. What's up with my camera? Oh, interesting. Okay. Well, I know what you're being fed, so you should be getting this information. Hopefully everything is working now. I don't quite understand that, what the problem was there. Yeah, my apologies. So here we have me getting back in my train of thought. Right. Under ambient conditions, reaction of nitrogen and oxygen to produce nitrogen monoxide, that equilibrium constant is 10 to the minus 31. Definitely the reactants are favored to the point that that reaction almost doesn't proceed. We'll look at what magnitude of equilibrium constant doesn't react, but that one's pretty close. So there's no reaction between nitrogen and oxygen to form nitrogen monoxide. Yet in the electric discharge at 25,000 Kelvin, it's actually slightly favored to the products. NO is the preferred entity at that temperature. Oxygen also decomposes to the point where you get diatomic oxygen forming atomic oxygen. At room temperature, that reaction doesn't occur. 10 to the minus 82 is well below a value that a reaction actually proceeds. Yet it is by far favored in the electric discharge. It is mostly atomic oxygen in that electric discharge. Now, after that lightning strike, the air inside the strike diffuses into the ambient air, and where there's oxygen present, and you have nitrogen monoxide reacting with oxygen to form NO2, that gives you a brown haze. But you also have oxygen reacting with atomic oxygen to produce ozone. And both of those, nitrogen dioxide and ozone, are by far the preferred product there. Where was I going to go with that? And, oh, yes, when you were to go for a walk after a lightning storm, and a lot of people like to do that, the NO2 gets rained out pretty quickly. There's still a lot of water vapor in the air, and it comes out. But ozone lingers for a while, a couple of hours. And so when you're walking after a lightning storm and you have that fresh, refreshing feeling, that it feels clean, you're actually smelling very, very low parts per million concentrations of ozone. Now let's look at mathematics associated with the equilibrium constant. So given the reaction R is in equilibrium with P, we are going to look at a number of different scenarios. And I'm going to flip over to the tablet in a few seconds, but this is what we're going to look at and try to get an understanding of how varying the chemical equation affects the equilibrium constant. and for whatever reason this thing seems to disconnect on occasion, that is a known problem, but hopefully we can work through it. So we have R in equilibrium with P. We're going to call that reaction 1. And K1 is simply P over R. If I reverse the chemical reaction and I end up with P in equilibrium with R, that's reversing it, we're going to call that reaction 2. And now we have K2 is R over P. How does this relate to K1? How do I relate K2 with K1?
It is the inverse.
It is the inverse. It is 1 over K1. Excellent. And that's all I want for the remainder of these. How do I go about doing this? The other way that you could write, we'll just leave it for that, like that for now. Next one is I'm multiplying through by a constant. So I have 2 reactants in equilibrium with 2 products. Call that reaction 3, and K3 is now P squared over R squared. Someone else? How does that relate to K1? It'll come back, I hope. Go ahead. It's K1 squared, as presented in the chat. Good. To do another one, I'm going to multiply through by 1/2, something else we commonly do. 1/2 R is in equilibrium with 1/2 P. Call that reaction 4. Equilibrium 4 is P to the 1/2 over R to the 1/2. And this would be equal to K1, the square root of K1. Excellent. Square root of K1, or K1 raised to the power of 1/2. Basically, what you're doing is whatever you multiply through by, you raise it to that power. You multiply through by 1/2, you raise it to the power of 1/2. And even this reaction right here is raising K1, to the power of -1. Because in order to get R and P, I'm really multiplying through by -1. I'm reversing it, which is multiplying through by -1. All right, now we're going to add a couple of equilibria together, and we have R is in equilibrium with P, that happened to be reaction 1, and we have P in equilibrium with Q, that's going to be reaction 5. K1 is P over R, K5 is Q over P. When I add these things together, I have R is in equilibrium with Q. What I want from you is what is K6 and how does it relate to the other equilibrium constants? What is K6 equal to, and how does it relate to the reactions above? You can use the chat, or you can use the talkie thingy. Anyone want to offer an answer to this, please? K6 is Q over R, that is correct. oops, wrong color. And how does that relate to the other equilibria? Anyone else? Jada has K1 times K5, right. It is simply the multiplication of those two. So when I add chemical reactions, I multiply their equilibrium constants. So to summarize what we did, when I reverse a chemical equation, I invert the equilibrium constant or raise it to the power of -1. It's the same thing. When I multiply through by a constant, I raise the equilibrium constant to that same power. And when I add chemical reactions, I multiply their equilibrium constants. Does anyone have any questions on that? We're good-ish? All right, let's look at an example. So we have got the reaction of nitrogen and oxygen and bromine forming NOBr. This, by the way, would be the formation reaction of NOBr. So it's a theoretical reaction. We want to determine Kc from the following data at 298 Kelvin. And so there's two reactions that are presented there. And part B is to determine Kp once we determine Kc. So let's go through and do that. So what we have, just rewriting out the reactions because it'll benefit me, 2NO is in equilibrium with N2 plus O2. And I am removing the states of matter just for convenience. Kc here is 2.1 times 10 to the 30. The second reaction was that of nitrogen monoxide plus bromine to form NOBr. And here Kc was 1.4 with units of liters per mole to the 0.5. Or 1 over concentration of the 0.5. At this stage, I mentioned before, I'm expecting you to be able to figure out what the units are applicable just by writing out the chemical equilibrium. I'm giving them to you here. If I now compare what I have to what I need, I realize that I want 1/2 nitrogen and 1/2 oxygen. So I'm going to take the first reaction and I'm going to multiply through by 1/2. And so that's going to give me NO is in equilibrium with 1/2 nitrogen plus 1/2 oxygen. And there appears to be a lag in the screenshot, so it'll be a few seconds for it to catch up. If I multiply through by 1/2, what I end up doing is I end up taking the equilibrium constant and raising it to the power of 1/2. Okay, so that gives me the new Kc of 1.45 times 10 to the 15. Now there is a lag here, and that lag is between my tablet and my computer. That one's my fault. The feeding to you, I don't know. I don't know what I just said, Benjamin. That was a while ago. Sorry. The next thing I need to realize is that nitrogen and oxygen are reactants in the overall reaction. So I'm going to multiply through by -1, or I'm going to reverse the reaction. And when I reverse the reaction, what I get is 1/2 N2 plus 1/2 O2 is in equilibrium. This is really slow. All right, I just reset it, so hopefully it'll be a little bit faster, I hope. Multiplying through by -1 means that I'm going to raise this to the -1, or take the inverse of it. And Kc for this reaction is now 6.90 times 10 to the -16. And it doesn't look like it's going to speed up anytime soon. Okay. Oh, there we go. Oh, that's interesting. Okay, I know where the lag is now. That's interesting. All right. Okay, good. Now we have those reactants, what we want, nitrogen and oxygen. The other thing we want is that last reaction, and it's actually unchanged. And so we have NO plus 1/2 Br2 is in equilibrium with NOBr. And Kc for this reaction is unchanged at 1.4 liters per mole to the 0.5. When I add these two together, I will get the reaction I want. We have nitrogen monoxide canceling out, and I have 1/2 N2 plus 1/2 O2 plus 1/2 Br2 in equilibrium. It should reset itself in a few seconds. There we go. There we go. And I now multiply the K values together, and Kc for this overall reaction is 9.7 times 10 to the -16 liters per mole to the 0.5. Good. Whew. Okay, that was the calculation of Kc. Are there any questions on that? If I now look at part B is the determination of Kp. And the relationship that we have is that Kp is equal to Kc RT to the delta N gas. There is the reaction, there is Kc. I'm going to put you into breakout rooms so that you can go through and calculate the KP for this reaction. So, and I'll give you about 2 minutes in the breakout rooms to do that. When I come back, please have KP with the units. And I will see you in about 2 minutes. Hey, Shamitha, you there?
Hello, I'm here.
Excellent. How's it going from your perspective?
For SI?
Well, no, the class. How is as a recipient of this? How is this presentation and the issues with whatever?
Yeah, I'm also seeing some of the difficulties. It was lagging a little bit for me, just visually, not in terms of audio.
Yeah, I don't understand that. The tablet lags on occasion because it's feeding the data to the computer, but I don't quite get why everything else was lagging. Like, you can see the tablet's having problems because it's refreshing, and rebooting my computer sometimes fixes that problem. This is the first time I've had it this term, so I just basically need to reboot the computer. So, okay. How about the rest of it? How is the presentation coming across to students and the like?
I think it's coming across. I think that they're definitely more comfortable with interacting now than they were a couple weeks ago. So hopefully that just continues to build.
Yeah, well, that's kind of what I'm hoping for. And using the breakout rooms, it takes time. It's unfortunate because it takes literally 20 seconds for it to actually put people in rooms and 20 seconds to pull them back or so. So that becomes a challenge.
Yeah.
Are you able to just, jump into that meeting this afternoon at 2:30?
I don't know if I'll be able to just because my schedule might not let me come in today.
That's fine. The reason I was asking, two things came out of it. If you're interested in what we discuss as a grad students, like with the TAs, if that's something that you're interested in doing, you can come and listen to our discussions there. But the other one is we are going to be talking about like the numbers in the office hours type of idea. I've had the TAs record their numbers, and I've asked you to provide me with your numbers as well. And so, if there needs to be any juggling or shifting, I would entertain that. Is more the point.
Sure. I think my attendance has been better than it was last semester thus far. But I think based on student feedback, if there's another time that would work better for them and that also works for me, I'm flexible in changing it based on student needs.
Most of the TAs are getting, between 7 and 10. I got to call everybody back, but most of the students at TAs are getting 7 and 10. There's a couple that are at 1, and I'm thinking, I'll give it another week, and then I will potentially move it at that point in time. All right, I'm going to bring everybody back. All right, everybody, I should be drawing you back from your groups. Dylan, to answer your question, it was actually given in the question. It was 298 Kelvin. Sorry, yeah. So the temperature was presented in the question as 298 Kelvin. My apologies. STP is fine. Okay. I know the temperature I actually added to the PowerPoint slide because I realized it wasn't there, so it isn't in what was presented to you. That was my error. But if you, as long as you use the number, it doesn't make a difference, okay? It was the process to go through and do this. And your value won't be much different than what we get here. Does anyone have a value for KP that they wish to share? You've worked in groups, you should be a little bit more comfortable with your numbers, please.
I got 1.95 times 10 to the negative 16 1 over 5.
Oh, so close. So close. Your number's right. What don't I like? The unit. What's wrong with the units? You said 1 over bar. It's not quite 1 over bar. Anyone else want to help him? What's the units here? Anyone? Well, if this is to the 0.5, clearly it's probably some unit, not integer values. If we look at n here, n is equal to 1.5, n over here, n is equal to 1. So delta n gas is equal to bar to the 0.5. Yeah, is negative 0.5. And so that means it is bar to the 0.5. And that is the value of Kp for this system. Good. Excellent. Given the time, that is it for today's class. When we come back next day, we're going to start looking at reaction quotient and getting into some truly setting up and solving equilibria problems. But for now, this weekend, you've got a quiz, a lab report, or lab quizzes and stuff. And you've experienced now a week of collaborate and 2 weeks of teams. So you kind of know the strengths and weaknesses of each of them. I will continue to post the videos up onto YouTube so people can go and grab them no matter what we go with, but I would really appreciate you providing your feedback. What is the strengths of teams? What is the strengths of collaborate in a survey that's going to come out this evening. And on Sunday, I will present the results of that survey to everybody. At this time, I'm just going to stop the recording and I will answer any questions that you have. So, yeah.